We're going to look at the equation that we solved in the previous video. I'm going to look at doing it a different way using Euler's, which means we're going to be using complex numbers. And I hope that eventually I can prove to you that using complex numbers and using Euler's relationship or Euler's formula will make this an easier problem, and especially when we get into more difficult problems. Now, if you haven't looked at the video regarding imaginary and complex numbers, and also the formula or the video for the exponential, which talks about Euler's, please do that. You'll need to look at those two videos so that you can appreciate how we're using it in this in solving this equation. Now, for the first step, and I keep emphasizing this, first step is solve the homogeneous. Equation. And we've done that. You can look at the previous video on first order homogeneous equation, and our solution for the homogeneous was CE to the 3t. Okay. Now, I'm going to rewrite our differential formula down here because we really want to look at some ideas here. And if you've had a chance to look at the video on linear time invariant systems and equations, you'll follow this conversation. If not, you need to look at that video. It's very important. So at this point, I have this equation, and it's a linear equation. It's also time invariant. So if it's linear and it is time invariant, I can use superposition, which means that I can add something to this equation. And as long as I can take the results out of the solution that would come up with this extra part, I can solve this equation by appearing to make it a little more difficult. So we're going to change this equation to make it into something a little more usable. And what I'm going to do is I'm going to take and add 5j sine 2t. Now remember the j operator, square root of -1, and it's this j operator that's going to make things remain separate, that's going to allow me to know what I need to take out so that I can get to the solution to this first equation that I wanted. Now remember that the cosine part is the real part, the sine is in the imaginary part. Okay, now this is just Euler's, this part here. I can simplify that down, and I'm going to have this brand new equation to solve. So this is, and let me stress this, this is a new equation. This isn't the original problem. This is a new equation that we're going to solve, and solving this new equation will get us to be able to solve the original equation that we wanted. So this is not the same. I want to stress that. It just happens that that equation, the first equation, is related to our new equation. Alright, so let's go ahead and solve this, and we need a non-homogeneous test solution. So our non-homogeneous test solution is going to have a form similar to this e to the 2jt. So I'm going to have a variable a, some constant, e to the 2jt. And now we're going to put this back into our new equation. Okay, now we need to take the derivative of this first part. Well, a is just a constant, so we'll take that out. Use the chain rule. Derivative of e to the 2jt, well, any exponential, its derivative is itself. And now I need to take the derivative of 2jt. I'm going to break this down into a couple little parts here to make it a little bit easier to follow. And now you'll notice that I have to get this derivative. Well, what do I do with this j? Just assume j is like any other number, a constant, and treat it that way when you do the derivative. So the derivative with respect to t of 2jt is just going to be 2j. So I'm going to have 2j a e to the 2jt minus 3a e to the 2jt is equal to 5e to the 2jt, and you'll notice that all of the e to the 2jt's will cancel out, and I'm going to write this in standard complex form, minus 3a plus 2ja is equal to 5. And I can distribute the a out. So a is going to be equal to 5 over negative 3 plus 2j. Now, let's simplify a little bit, because we like to have the j in the numerator, not the denominator. And the way we're going to do that is use the complex conjugate. So our complex conjugate Remember, we changed the sign of the term that has the j in it, so we have minus 3 minus 2j, and we're just going to multiply this term for a by 1 in the form of minus 3 minus 2j over minus 3 minus 2j on the top. And this is going to be minus 15 minus 10j over, and now I've got minus 3 times minus 3 is 9, and I'm going to have plus 2j minus 3j is going to be minus 6j, and minus 3 minus 2j is going to be plus 6j, and plus 2j times minus 2j is going to be minus 4j squared. That's going to be minus 15 minus 10j over 9 minus 6j plus 6j, that's going to go away. I have a minus 4j squared. J squared is equal to negative 1, so that's going to make this 9 plus 4, and that gives me minus 15 thirteenths minus 10j thirteenths. Now, let's put this back into our non-homogeneous equation. And let's convert this back into Euler's. Go the opposite way. And that's just going to be cosine 2t plus j sine 2t. And I should use a bracket here. Okay, now we'll do the distributive property. So I'm going to have minus 15 thirteenths cosine of 2t minus 15 thirteenths j sine of 2t minus 10j over 13 cosine of 2t minus 10 thirteenths j squared, right? J times j sine of 2t. And now I'm going to group real and imaginary parts. So I'll have minus 15 thirteenths cosine two t, and my other real part is going to come from this last term where I have a j squared. J squared is negative 1. Negative 1 times this will give me plus 10 thirteenths sine of 2t. And then I'm going to have my j terms here, and I'm going to put plus, I'm going to just to pull the j's out of both of those terms, and I'm going to have minus 10 thirteenths cosine 2t minus 15 thirteenths sine of 2t. Now remember, we said when we started out that this first problem, the one that we wanted to find, we just were looking for the real part of Euler's, and we had added in this imaginary part so that we could use Euler's. So now that we're at the end, since the cosine is the real part, we only need the real part of this solution. And so our solution is going to equal the homogeneous solution plus the real part of our non-homogeneous, and this is for the Euler equation. And so our solution is going to be CE to the 3t minus 15 thirteenths cosine 2t plus 10 thirteenths sine 2t, just like we got in the last video. Now there's something interesting here. If I were to take the imaginary part of this and come up with this formula for our solution, that would have to be a solution to something. And you can verify this by putting back into this equation this differential equation. This is a solution to this equation. This on this left one is the solution to so you notice if I take the real part, I get the solution to the differential equation that has the cosine in the right part of the equation. If I take the imaginary part of this Euler solution, I get the solution to the differential equation if it was a sine on the right side of the equation. So you're actually getting two solutions to two different differential equations just by solving one equation that uses Euler's relationship.